All right, PreCalc. You survived the first part of the chapter, just graphing your three conic sections. Don't forget there are four. There's the circle we've done previously, the ellipse, the hyperbola, and the parabola. And today we're going to do what's called rotation of axes. And a couple extra notes here about just looking at different equations first and identifying which type of conic section we have. So if we have what we call a non-degenerate conic section, we get this standard form. And this standard form should look familiar to you because this is usually what I've been giving you when you need to complete the square. You might have an x squared, a y squared, an x, a y, and a constant, and we move them around, we can complete the square, and we can graph the conic section. So we have slight differences between these equations when we do this. If you happen to see a plus and A and C are both positive, if A and C are the exact same number, it's going to end up being a circle. Okay, and the key on that one, if it's a circle, remember that you want it equal to r squared, not equal to 1. So just kind of a heads up on that one. But for right now, we just want to be able to look at an equation and tell what it is. If it says, and this is hard to say, a parabola if A times C equals 0. Okay, basically, a parabola, this is how I remember it, if only one squared term. Okay, so maybe only x squared or only y squared, but not both of them. That's why it says if you multiply by, if one of those numbers is missing, an x squared or a y squared term, then you get the parabola. You have an ellipse if A does not equal C, but A times C is greater than 0. So basically between your x squared and y squared, if it's a plus, but your numbers in front of them are different, then you're going to have an ellipse. If A times C is less than 0, so basically if you have an x squared minus a y squared, or don't forget, it could be a y squared minus an x squared. If there's the minus between them, and by the way, the numbers can be the same or different, then you're going to get the hyperbola. So what this quick note tells you is if you can just look at an equation, you don't have to do the full completing the square to figure out what we have. So I have a few examples for you here. On example 1, identify each conic section without completing the square. So really my two things I'm looking for every time are my x squared and my y squared. So in this one I see my x squared, I see my y squared. Are they the same number? No. So it can't be a circle. And between them I see a plus with different numbers, so that leads me to say that one has to be an ellipse. The second one, I find my x squared, I have no y squared. So because I only have an x squared, it has to be a parabola. On my second one, I notice one, I have an x squared and y squared. They're not side by side. I'd like them side by side. So I'm going to add this y squared and move it to the other side. So I end up with an x squared plus a y squared minus 8x plus 11. And really those don't really matter because they are both plus and they're the exact same coefficient of 1. That leads me to believe this would make a circle. And finally on the last one, I find my x squared and my y squared. They're side by side. There is a minus between them. As long as there's a minus, this will always be an hyperbola. Okay, and that is the easy part of our lesson today. Let's move on to what can get kind of complicated, and I'm really kind of scared to be writing this here on this with a stylus on an iPad, but I am going to do my best to keep this legible. That's all I can promise you is I'll try my best. Okay, so a quick note on the bottom here, and then I go to the next page because I found that I kind of need a lot of paper for this. So everything we've graphed so far has been great. Our axes are always horizontal or vertical every time for everything. For my ellipses, for my hyperbolas, even for the parabolas, my directrix was either a horizontal or a vertical line. That's not always true though. So what we have now, those were what we called, the earlier ones, the non-degenerate. Now we're going to have what we call degenerate cases. And the difference you're going to see in this equation is this little term right in the middle. In between my x squared and my y squared, I now have an xy term. If you think about that, I can't really complete the square because I've never had something with both variables on the same term. But now that one's going to show up. And you'll notice if you look back, we were always missing that coefficient of big B. Well, here it is now because it fits in between my ax squared and my cy squared. When that term is present, it means that my graph has been slightly rotated, maybe a lot rotated, and it's no longer exactly horizontal and vertical with the origin. So that's what we have to work with today, is we're going to actually rotate our graphs, and we're going to turn our like transverse axis or our directrix or whatever we need to work with, we're going to turn it, and then we're going to be able to graph our shape. But we won't know until we do all the math. So what we're doing today is called a rotation of axes with our conic sections. So let's go to the next page, and we're going to do our best to see the math that goes with this and to work through it. Okay, so lucky for you, obviously when you're doing all this at home by yourself, you get to use your notes, and you know you have your notes. So again, the more you familiarize yourself with this, the better you're going to be able to repeat it for me on a quiz or test. So this rotation of axes formulas, and it's important that you kind of recognize this, because if all I ask you for is a rotation of axes formulas, all I'm asking you is for your new x and y, basically, okay? I'm not asking you for the full rotation of everything, okay? So what we're doing is we're taking a ordered pair of xy, and we're going to rotate it on our graph. So to do that, we need an angle, okay? So you'll notice here that if I'm going to rotate x, I'm going to end up with this x prime times the cosine of theta minus y prime times the sine of theta. So it's rotating it using the cosine and sine to move that, okay? Same thing with the y. I'm doing an x prime with the sine of theta, y prime with the cosine theta. Theta is our angle of rotation. And I will be honest, our angle of rotation should be between 0 and 90 degrees because, and then we could go past that obviously, but we'd kind of end up with the same pattern over and over where we rotate it, okay? So our first one we're going to do is, I'm going to do a full out problem, but I want to stop when we have that rotation of axes so you can see that. We're going to write this equation, 13x squared minus 6 radical 3xy plus 7y squared minus 16 equals 0, in terms of the rotated system. When we do that, we're going to see a lot of these primes because we're going to use this angle of rotation. Now, they did give us the angle right now is 60 degrees. That's how far we're going to rotate off of our normal, nice perpendicular, horizontal, vertical lines. We're going to rotate at 60 degrees. So, a couple things to start with. We need to find our new x and y as we do this work. So, don't forget at 60 degrees, oh yeah, that unit circle. What's my ordered pair at 60 degrees? So, get your hand moving up a little bit. I believe if we check our unit circle, that's going to be at 1/2 radical 3 over 2. Okay? Don't forget that our x value is always goes with the cosine, and our y value here goes with the sine. Okay? Those are going to come in handy as we find our rotation of axes formulas. Okay. So here we go. To find our x, we're going to do x equals x prime cosine theta minus y prime sine theta. You probably noticed I made my pen a little thinner tonight so that I can hopefully fit everything on the page. I don't know if it'll help, but we'll try our best. Okay, so my new x is going to become x prime. And by the way, that's not going anywhere. It just is part of my expression, part of my formula. The cosine of 60 degrees now, because that's my angle of rotation, minus y prime, the sine of 60 degrees, because again, that y prime is not going anywhere either. All right, let's do what we can. I don't know my x prime, but my cosine of 60 is 1/2. My y prime, my sine of 60 is radical 3 over 2. Now, can I simplify that? There's not a whole lot I can do. What I'm going to just do here is I'm going to do x prime times 1, so I'm going to get x prime over 2 minus, and I'm just going to pull this y prime up here with 3. Now I'm going to express my x now on the rotation. So I've rotated that x 60 degrees, and this is the new way I'm writing my x. Okay, so let's do the same for y. So y is x prime sine of theta plus y prime cosine of theta. And once again, that primes are going nowhere. They're part of our formula. X prime times the sine of 60 degrees plus y prime times the cosine of 60 degrees. So once again, the sine of 60 is radical 3 over 2. And the cosine of 60 is 1/2. And again, I'll try to simplify as best I can. I can do x prime radical 3 over 2 plus y prime, let me lift that up a little bit, y prime over 2. Okay, this right here, these two things, hopefully I didn't make it so I can't read them anymore, that is what I call my rotation of axes formula. So if I ask for just that on a quiz or test, that's all I'm asking for. You just stop there on your x and your y. It tells me what my new x and new y are on the rotation, okay? So I've rotated just my ordered pair. Now I'm going to go through and I'm going to do the second part of my problem, which is to write the equation in standard form. And as we work through this math, we're going to be able to transform this equation so we can actually see, is this degenerate system now, is it going to be a circle, an ellipse, a hyperbola, or a parabola? Right now, when we look at it, this 13x squared minus 6 radical 3xy plus 7y squared minus 16 equals 0. We can't go back to what we did at the beginning and just say, well, I have a 13x squared plus a 7y squared, so that's an ellipse. We don't know that because of this extra term in there with that xy. Okay, so let me lift my paper a little bit because we're going to need all the space we can get. And unfortunately, I can't increase it on the horizontal, but I'm going to, oops, I need to see my equation. There we go. Okay. So here we go. We're going to now plug our new x and our new y into our equation, and we're going to do the math to see what happens. So this is my equation up here, and I'm plugging in for every x, I'm plugging in this rotated x, and for every y, I'm plugging in this rotated y, and we get to do the algebra that goes with it. So here we go. First one, 13, and it's x squared, so that's going to give me x prime over 2 minus y prime radical 3 over 2, and the whole thing squared. Then next plug in minus 6 radical 3 times the x, so my x is x prime over 2 minus y prime radical 3 over 2 times the y, and my y is x prime radical 3 over 2 plus y prime over 2 plus 7y squared, so 7, and now my y squared, which is x prime radical 3 over 2 plus y prime over 2, and that is squared because my y was squared, minus 16 equals 0. Just to help me out right now, I'm going to move that 16 to the right side right away because it has nothing to do with all the rest of this beautiful algebra. Okay, we found our new x and y, the rotated ones. We've plugged them in for our old x's and y's, and now we're going to work through our rotated system here. Okay, algebra, algebra, algebra. Can't stress it enough. That's what we're doing. We have to be careful. The primes are important. We need to think about what happens to each term when we square them, when we multiply, all of that good stuff. Okay, so this first term, it says it's squared. That really means that it's x prime over 2 minus y prime, can't read that, so we're going to try that again, minus y prime radical 3 over 2 times itself. That's what it means to square, right? X prime over 2 minus y prime radical 3 over 2. Okay, don't forget this 13 is a coefficient, so I'm going to put 13, and now I'm going to square those terms, okay? So first, x prime over 2 times x prime over 2 is going to give me x prime squared over 4. Okay, that was my first. Outsides. So when I multiply x prime over 2 times negative y prime radical 3 over 2, I'm going to get a negative x prime y prime radical 3 all over 4. Okay, that was first outer. I'm in the inner. Okay, inner. So my 2 in the middle there. And I'm going to get another x prime y prime radical 3 over 4. And then finally the last two, a negative y prime radical 3 over 2 times a negative y prime radical 3 over 2 will give me a positive Radical 3 times radical 3 is 3y prime squared all over 4. Alrighty. There's my first term. Okay, kind of. I'm now on my middle ones. I'm right here. So I don't have to rewrite them because they're there. So I have a negative 6 radical 3. And now when I FOIL these two terms out, so x prime over 2 times x prime radical 3 over 2 will give me x prime squared radical 3 all over 4. If you can follow me, because it will save me a lot of work here, when I do my out and my inside, I'm going to get, never mind. Let me just do it. Okay, I'm confusing myself right now. Okay, outsides, x prime over 2 times y prime over 2 will give me a positive x prime y prime over 4. Insides, because I have two radical 3's, by the way, that's going to be negative because one's negative, one's positive. So I'm going to get negative 3x prime y prime over 4. And my last two is going to give me another negative y prime squared radical 3 over 4. All right, that's my second big term there. All right, on my last one, I'm going to end up foiling again this one. I'm kind of running out of space, so I'm going to stagger this just a little bit. I'm going to have plus 7. And when I FOIL this, so remember this is an x prime radical 3 over 2 plus y prime over 2 times itself, x prime radical 3 over 2 plus y prime over 2. That's a y. All right, so first two. Those radical 3's are going to become positive 3 x prime squared over 4. Outsides are going to give me positive x prime y prime radical 3 over 4. Insides are going to give me positive x prime y prime radical 3 over 4. And the last two will give me y prime squared over 4. All right, and don't forget that all equals 16. Okay, are we confused yet? I promise you that's a 16. Okay, here's a huge thing right now that we can do a little bit to clean some things up. Absolutely everything in my brackets is over 4. Okay, so I have the option right now of multiplying my entire equation by my denominator. I do that all the time in algebra, right? Now, here's the deal. Most of the time, if I decide to multiply my entire equation by a number, I usually take it times the outside number. I don't want to take it times the outside number. This 4 is going to cancel all of these 4's, all of these 4's, and all of these 4's. So as long as you have the same denominator on absolutely every one of those terms, it's going to cancel everything. Okay, so let me do a little cleaning up now. Now I have 13, no more fractions, which is great. Inside this bracket, I have an x prime squared. These two middle terms actually match with a negative, so they become negative 2x prime y prime radical 3. That's not even very pretty. I probably should have pulled the radical 3 up front, but we're going to leave it for right now. Plus 3y prime squared. I have minus 6 radical 3. All right, does anything in here match? Well, the two middle terms can combine. They're like terms. So I have an x prime squared radical 3, a plus x prime y prime minus a 3 x prime y prime will make a negative 2 x prime y prime minus a y prime squared radical 3. And then I get a plus 7. Let's see, like the same sign. So I get a 3x prime squared plus 2x prime y prime radical 3 plus y prime squared, and the whole thing equals careful here, 64, because this was a 16. I know you can't read that 16 because I can't get it to write right there. But this 16 had to get multiplied by my 4 as well because everything in the equation got multiplied by that. All right, let's see if I have more paper. I do. Here we go. Just now I'm going to take my coefficients into everything to see what I can start doing. So I have a 13x prime squared minus a 26x prime y prime radical 3 plus a 39y prime squared. I know it looks like a coefficient of, or an exponent of 12 with the prime and the squared, but trying to do the best I can here. Minus, okay, this 6 radical 3 times a radical 3. The radical 3's will multiply and get 3 times 6 makes it minus 18 x prime squared minus the middle term there or it'll become plus 12 radical 3 x prime y prime plus, and again another radical 3 times radical 3 will give me a positive, I keep saying positive 3, but the number 3 times 6 will give me 18 y prime squared plus 21 x prime squared plus 14 x prime y prime radical 3 plus 7 y prime squared equals 64. I really hope I didn't make a mistake in there. Okay. As messy as this is, some beautiful things are happening here. Okay, I have a 13x prime squared. I have a negative 18x prime squared. I have a positive 21x prime squared. I believe that's all of my x prime squareds. And if I add those coefficients, 13 minus 18 plus 21, I believe I get 16 x prime squared. All right, joining like terms. All right, these beautiful radical 3's with the x prime, y prime. So I have a negative 26. Notice I wrote them different ways here. Positive 12 radical 3. And I have another one over here. Positive 14 radical 3. Negative 26 plus 12 plus 14. They cancel. They're gone. The ugliest terms on there all cancel. Beautiful. All right, we're left with some y squareds, y prime squareds. I have a positive 39, a positive 18, and a positive 7 y prime squared. 39 plus 18 is 57 plus 7 is 64. And the whole thing equals 64. All of that, and this is what it simplifies to. All right, so now we kind of have this equation we're starting to get familiar with. Can it be a circle? No, because my two coefficients don't match, but I do have a plus, which means I probably have an ellipse. So let's get it in the standard form of an ellipse, which means I need it to equal 1, so I'm going to divide by 64. And remember, we'll simplify that fraction, so I'm going to get x prime squared over 4 plus y prime squared over 1 equals 1. And that definitely fits the equation of an ellipse. So just to kind of give you a visual of what happened here with my conic section, I have my normal coordinate plane. But what happened is I rotated it 60 degrees. So if you think of your rotation here of about, wow, what's the chance I can draw anything semi-accurate here? I have this rotation line kind of 60 degrees right here, okay? So I basically have taken my ellipse and I'm going to turn that center point here and it kind of goes up one, and I kind of turn this ellipse going this way, okay? Notice my major axis is out 2 on each one. My minor's up and down 1. That's what I've done with this equation. When we looked at the equation at first, we probably didn't know it was going to be an ellipse. But as we work through this algebra with this rotation, we get our rotated ellipse. Are we having fun yet? All right, let's go to the next page. Okay, I kind of broke this one apart a little bit. Let me make sure I'm on the same page as you are. Sometimes what we have to do is find our angle of rotation because we're not always given it, okay? And our equation actually tells us our angle of rotation, even though we don't always see it, we can find it. And once again, we see this degenerate equation, which says that I have this a x squared, the cy squared, and because the bxy is in there, we know that we have a rotation. And we have this formula of cotangent 2 theta equals a minus c over b. That will help us find our theta, or our angle of rotation. So we can use this formula in combination with our unit circle, with a calculator, with a triangle, whatever we're going to work with to find our angle of rotation, okay? So for example 3 here, we're going to find the angle of rotation for 3x squared minus 10xy plus 3y squared minus 32 equals 0. And for right now, we're just finding our angle of rotation, okay? So we're going to use this equation of cotangent of 2 theta equals a minus c. Well, a is our coefficient in front of our x, which is 3, minus our c, which is in front of our y squared, so that's a 3, all divided by our b, which in this case is negative 10. So I get cotangent of 2 theta equals 0 over negative 10. Well, 0 divided by negative 10 is obviously just 0. Okay, so this is where we take a step back. We did this back in chapter 5. We say, okay, cotangent of 2 theta, okay? So remember, we can't always solve when it's there. So I'm going to do a little substitution. I'm going to say y equals 2 theta, and I'm going to say cotangent of y equals 0. So I'm asking myself, where on my unit circle is my cotangent 0, okay? So y is asking, where is your cotangent 0? Now, of course, it's cotangent, which we didn't usually do. So that's saying the same thing as saying, where is your tangent, like 1 over 0, or undefined, okay? So this is the same thing as the tangent undefined. Well, where in our, let's keep it in our first quadrant unless told otherwise, where in our first quadrant is our tangent undefined or our cotangent at 0? And the answer for that would be 90 degrees. Okay, that's when our tangent was undefined. Okay, but remember, y equals 90. Y was my substitution. I'm going to substitute back 2 theta equals 90. That means my theta equals 45 degrees. So in this case, if with this equation, its angle of rotation is 45 degrees. Okay? And now it says write the appropriate rotation formulas so that in the rotated system, the equation has no x prime, y prime term. So we're going to go through and we're going to do the whole thing we just did with our last equation. All right, you ready for this? So we're going to start by starting with our x's and our y's. So don't forget that x equals, and I have to, it's right up there, right? X prime cosine theta minus y prime sine theta. And of course, y is going to equal x prime sine theta plus y prime cosine theta. All right, so we're doing x prime cosine of 45 degrees minus y prime sine of 45 degrees. And taking kind of a step back, don't forget 45 degrees is that ordered pair, radical 2 over 2. Cosine and our sine is actually the same thing. So I'm going to have x prime times radical 2 over 2 minus y prime times radical 2 over 2. And that's where I'm going to be. Now, a couple ways we can do this. We can leave this as is. We can do x prime radical 2 over 2 minus y prime radical 2 over 2. As we work through some of this, because of all the radical work, sometimes I pull the radical, I factor it off, and so I might write it radical 2 times x prime over 2 minus y prime over 2. So just kind of giving you some options here. Remember, there's a lot of algebra we're going to do with it, so whatever feels comfortable for you as a fraction, as long as you keep your algebra true, okay? So let's do our y here. I'm going to have x prime the sine of 45 degrees plus y prime the cosine of 45 degrees. Gives me x prime of radical 2 over 2 plus y prime radical 2 over 2. And again, we can leave it two different ways here. I could do x prime radical 2 over 2 plus y prime radical 2 over 2. Or I could write it y equals radical 2 times x prime over 2 plus y prime over 2. Okay, so there is our, we call those the rotation formulas, but it asks us to write, I think we can stop there, write the appropriate rotation formulas. So this is where we can stop. And again, I'll take these either one of these ways, okay? All right, and I know I'm sounding hesitant here. I found my notes to give you, and the notes are different than what I'm giving you, so all of a sudden I'm second guessing myself, but I think that's where we want to stop with them there. Okay, let's go on to 4, page 4 here. And this one is a big one again. Okay, we've got a lot of work, we've got a lot of primes coming through, so we're going to do this. So we're going to start right now with just the rotation formulas. So this is just taking and finding our angle of rotation so that we can write our new x and our new y with that rotation. All right, so we are using cotangent 2 theta. I'm going to kind of come over here because I kind of know where this is going and I want some space here. Cotangent 2 theta from our notes on the other page was a minus c over b. So I'm going to get cotangent of 2 theta equals my a, which is 1, minus my c, which over here is a negative 2. Make sure that negative comes with it, over b, which is 4. So I get cotangent of 2 theta equals 3 over 4. All right, now you're probably already thinking, even if I flip this, there's no tangent of 3 over, or a 4 over 3 on my unit circle, and you're right, there's not, okay? So if you remember from back in chapter 5, this is where we go and we draw this nice triangle in our first quadrant, and remember it always uses this y-axis. I make my triangle coming off my theta over here, only I'm going to make this 2 theta because that's what I'm working with, and it says that 2 theta, my cotangent was 3 over 4. Okay, so think about it. Tangent is opposite over adjacent. So cotangent is adjacent over opposite. So from my 2 theta there, my adjacent leg is 3, my opposite leg is 4. And if you wanted to, you could go ahead and you could write down your, find your hypotenuse over here is 5. So at least we have a nice 3, 4, 5 triangle. Okay, once again, this is pulling back from our chapter 5 notes when we are not on the unit circle and such. So just note here from this, I'm going to go ahead and find the cosine of 2 theta. Okay, and by the way, I'm using some double angle work. So if you go find that note sheet from chapter 5, this is where I'm pulling some of this from. Cosine of 2 theta. So my 2 theta is this angle. Cosine is adjacent over hypotenuse. So my adjacent is 3. My hypotenuse is 5. So that's a sure fact because I get that from my triangle, okay? So now when I go to find my cosine of theta, I'm going to my double angle, or now I'm going to my half angle formulas because this was cosine of 2 theta. I only want cosine of theta. So if you, like I said, go back to that chapter 5 formula sheet, if you can dig that out of anywhere. Trying to think. I have one sitting here in my notebook, and it is blue. So there's a good chance your chapter 5 identities is what it says at the top, and it's probably blue. So go look for that if you can. If not, just follow along here. I'm doing a half angle, okay? And it said cosine of x over 2. Well, remember, I had 2 theta. When I divide that by 2, I'm just at theta. And what it tells me I have is a positive or negative, and because we're in the first quadrant, we're going to stay positive. And we do a 1 plus cosine of 2 theta, and this is part of the formula, divided by 2. And the sine of theta is going to be, I believe it's 1 minus, 1 minus the cosine of 2 theta all over 2. Okay, and this is from the half angle formulas from chapter 5. That's where I'm getting these from. Notice the only value I need to know is the cosine of 2 theta. I have the cosine of 2 theta, so I can use these half angle formulas because I have that. So here we go. So my cosine of theta is going to be 1 plus 3/5 all over 2. Just some algebra, right? 1 is 5 over 5, plus 3 over 5 makes 8 over 5 all over 2, which is going to be, make sure I'm doing my math right here, 8 over 10, right? Which simplifies to square root of 4 over 5, right? If I want to simplify that, the square root of 4 is, I'm trying to find some space here, cosine, the square root of 4 is 2 over square root of 5. And if I rationalize that, I'm going to get 2 radical 5 over 5. Wasn't that pretty? Okay, sine of theta. What's the chance I have enough room? 1 minus 3 over 5 over 2. Well, again, 5 over 5 minus 3 over 5 will leave me with 2 over 5. 2 over 5 over 2 is the same as 2 over 10, which is the same as 1/5. And similar to what we just did, I'm going to get 1, and I'm going to rationalize it right away, 1 radical 5 over 5. So there's my sine of theta, is radical 5 over 5. My cosine was 2 radical 5 over 5. Okay. That was fun. Angle of rotation. If it's not on the unit circle, we have to go this method. I'm not going to tell you I'm going to throw one of these at you, but I do want you to see that this is a possibility and you may have to do one of these, okay? But keep in mind that that's kind of where we're going with that. Okay, now I needed to find my rotated x and my rotated y. So my x is going to be x prime cosine theta minus y prime sine of theta, right? That's my formula. And so now I can plug in these beautiful values, right? So my cosine is 2 radical 5 over 5 minus my y times the sine, y prime times the sine, which is radical 5 over 5. Okay, for ease, I think because, again, I've done some of this algebra before, I'm going to pull that radical 5 off of both of them. So I'm going to pull radical 5 off, and I'm going to leave 2x prime over 5 minus y prime over 5. That's how I'm going to write my x from now on if I have to write that, okay? So similarly, let's do my y. So for y, don't forget the formula is x prime sine theta plus y prime cosine theta. So using these values we got x prime times the sine of theta, which is radical 5 over 5, plus y prime times the cosine of theta, which is 2 radical 5 over 5. And y is going to, once again, I'm going to pull that radical 5 out, factor it off, and I'm going to leave x prime over 5 plus 2y prime over 5. All right, so there's my y value. And now, those are my appropriate rotation formulas, so that's what I would stop at if that's all I asked for was a rotation formula. Now for example 5, it says keep going and let's plug it into the equation and let's figure out which conic section we have. Okay, so we're going to keep moving with these beautiful numbers and see what we can find. Oops, I guess I'm going to need to see those numbers. Okay, let's attempt another color here just to keep this straight. Okay, here we go, plugging in to our formula right here. So I have an x squared, so I'm going to take radical 5, parenthesis 2x prime over 5 minus y prime over 5. And the whole thing's going to get squared, plus 4 times the x, which is radical 5 times 2x prime over 5 minus y prime over 5, times y, can't forget the y, which is radical 5 times x prime over 5 plus 2y prime over 5, minus 2 times my y squared, and my y squared is radical 5, parenthesis x prime over 5 plus 2y prime over 5, the whole thing squared, and it's going to equal 1 when I send that 1 to the right side. Okay, so some advantages here to pulling those radical 5s out front. When I square, I need to square that, and then I need to square what's in the parentheses. So when I square radical 5, I get 5, and I don't have to see that radical anymore. Now I need to FOIL this one out. Okay, so if you can follow me on this FOIL, okay, this is what I'm going to do. My first two would be 4x prime squared over 25. Wow, the writing's terrible. Okay. In the middle, when I FOIL, I'm going to get two terms that are negative 2x prime y prime over 25. So if I multiply that by 2, I'm going to get negative 4x prime y prime over 25. And then my final on my last two are going to be a negative y prime over 5 times a negative y prime over 5 will be a positive y prime squared over 25. Okay. In the middle, I'm going to get that 4 out front. When I multiply this parenthesis times this parenthesis, I'm going to get a 5 when I multiply radical 5 times radical 5. And now I'm going to multiply or FOIL these two parentheses together. Okay, I probably should call these brackets. First, 2x prime over 5 times x prime over 5 is going to do 2x prime squared over 25. Outsides are going to give me a positive 4x prime y prime over 25. Insides are going to make a negative x prime y prime over 25. And the last two are going to make a negative 2y prime squared over 25. All right. Last set back here, that's what I'm on right now. I have a negative 2. Once again, when that radical 5 is squared, it's just going to make a 5. And I'm going to FOIL out this ending binomial here. So I'm going to get an x prime squared over 25. Two middle terms will make 2 of the 2x prime y prime over 25. So 2 of them will be 4x prime y prime over 25. And squaring that last term will make it 4y prime squared over 25. And the whole thing equals 1. Okay, so just like my earlier example, every fraction on this whole thing has a 25. So if I multiply everything by 25 and I carry the 25s into the parentheses, instead of using them with the coefficients outside, I can get rid of these ugly fractions. So I'm going to multiply my entire thing by 25. That'll cancel, that'll cancel, that'll cancel. Don't forget that's going to multiply this outside 1 by 25. Okay, so I'm going to also on this step, just to save myself time, distribute my coefficients here. So I'm going to get a 20 x prime squared minus a 20 x prime y prime plus a 5y prime squared plus, okay, notice this is 20 into everything in here. So I'm going to do 20 times this 2 will make it 40 x prime squared. Just notice these two are like terms, so I'm going to combine them and make them 3x prime y prime. And then times the 20 will make that plus 60 x prime y prime. And that 20 times the negative 2 will make negative 40 y prime squared. On to my last parenthesis set here, I have a coefficient of negative 10, so I'm going to get negative 10 x prime squared minus 40 x prime y prime minus 40 y prime squared. And the whole thing equals, don't forget, 25, because I multiplied that 1 times that 25 that canceled all those denominators. All right, this is where we cross our fingers that we did all of our math correctly and we can get some things to join up and things to cancel. Okay, 20x prime squared, 40x prime squared, minus 10x prime squared. So that's 60 minus 10, so I get 50x prime squared. All right, I get a negative 20x prime y prime, positive 60x prime y prime, negative 40x prime y prime. They cancel. And I'm going to be honest, guys, if you do your algebra correctly, your x prime y primes always cancel, which is what's beautiful. All right, what do we have left? Positive 5y prime squared, negative 40 prime y squared, negative 40 prime y squared. That makes a negative 75 y prime squared equals my 25. All right. All of that came down to this. What's nice is I don't have any x prime y primes anymore. I just have these two. It looks like because I am different coefficients and the more I'm tracking, it looks like what I'm going to have is a hyperbola that's been rotated, and I always have to have it equal to 1. So I'm going to divide by 25, and I'm going to get a 2x prime squared minus a 3y prime squared equals 1. And it's my hyperbola. Now, this doesn't look like our normal hyperbola because we're not used to actually whole number coefficients. So just think about this. I really want x prime squared by itself on the top. So how could I get rid of 1 of 2, okay? I really want a denominator, okay? I can always put 1s down there, but I really don't want that 2 on top. What can I do to 2 to get rid of it or to turn it to 1? Well, I can multiply it by 1/2. And what I do on the top, if I do it on the bottom, I'm going to have an equivalent equation, okay? Or equivalent fraction, more like it. Okay, so these two will cancel, and I'm going to be left with x prime squared over 1/2. Not a beautiful a squared, but that's what it is. So over here, I don't want this 3, so I'm going to multiply it by 1/3 to turn it into a 1. I multiply this by 1/3, those cancel. I'm left with minus y prime squared over 1/3 equals 1. So to be honest, my 1/2 is my a squared, my 1/3 is my b squared, and I could use it to graph this. Now, my angle was not pretty. It was not an angle that I even really know what it is exactly. By the way, I could go back and I could take the inverse sine of radical 5 over 5, and I could find the actual angle. It's not going to be something pretty that comes from our unit circle, but it is an actual angle. So again, this hyperbola got twisted, and my curves would still go out. Obviously, they'd go more left and right on my tilted axis because my x comes first. All right, are we overwhelmed yet? One more page, and believe me, it's not that bad. Let's do the last page. All right, so we started our notes saying that if we just know the kind of how to look at an equation and know some telling signs, what kind of equation will it turn out to be? We were able to do that with our non-degenerate. And remember, the key is on a non-degenerate is we do not have an xy term in it. But the question is if we do have an xy term in it, can we still have a quick, kind of like a Cliff Note version of can we look at an equation and tell? So this is our quick Cliff Notes basically on saying if we have that xy term in the middle, can we quickly determine if it's going to be a parabola, ellipse, or circle, or hyperbola? I wanted to make sure you know that on this one right here, when it says ellipse or circle, you're never going to tell me which of the two. You will simply tell me it's an ellipse or a circle, and you leave it at that. You're not going to decide between the two. So we could determine if it's a parabola if we do b squared minus 4ac equals 0 exactly. It's an ellipse or a circle if b squared minus 4ac is less than 0 or negative, and it's a hyperbola if b squared minus 4ac is greater than 0. Quick note, where does b squared minus 4ac come from? If you remember, it's our determinant in our quadratic formula. It's the one underneath the square root, right? That's our determinant. So again, kind of ties back in our quadratics here. Because we see the squared terms, that's where it kind of comes from. Okay, so basically, if you're trying to think of this, think, hey, I'm finding the determinant or similar math for the determinant to figure out what this is going to end up being, a parabola, an ellipse, a circle, or hyperbola. Okay, so 3 examples. Let's do them quick. And what happens here is we don't have to do all of that work we've just been doing to see what this equation ends up being. So remember, a is what's in front of my x squared, b is what's in front of my xy, and c is what's in front of my y squared. And be careful, make sure you grab your actual signs that go with those as well. So here we go. We're going to do every time b squared minus 4ac, and we're basically checking, does it equal 0? Is it negative, less than 0, or it's a positive value which is greater than 0? So I get 9 for my b, minus 4 times my a, which is 2, times my c, which is 14. Well, 9 squared is 81. 4 times 2 is 8, times 14 is 112. And I'm going to be honest, I don't even care what the number is. I can tell right away that thing's going to be negative. So this equation, when I do all my rotation, would end up being an ellipse or a circle. And remember, you are not going to choose between those. You are simply going to tell me that's an ellipse or a circle, and then you stop. That's all you have to tell me, okay? And if I needed to, then it gives me that hint that if I did all the math, it should come out to one of those. All right, so let's check B. Right now I have my x squared minus 4xy, that's my b, in front of my y is my c. So again, b squared. So I get negative 4. I'm squaring it, minus 4 times my a, which is 1, and my c, which is positive 4. That gives me a 16 minus 4 times 1 times 4 is 16. I get 0. And anytime I end up with 0, I know that if I did all my rotation work, this is going to be a parabola. All right, one more to go. I wonder what the answer might be. A in front of the x squared, b in front of my xy, c in front of my y squared. And quick note, if they didn't happen to put our equation in this order, put it in the order of the x squared, the xy, the y squared, the x, the y, the constant equals 0 to be able to check this, okay? All right, b squared, that's a negative 1 there, that invisible number 1 squared, minus 4 times my a, which is 1, times my c, which is negative 4. Negative 1 squared is 1. 4 times 1 times negative 4 is negative 16 minus a negative 16 makes it positive. And again, yeah, it's positive 17, but the most important thing is it's positive. That's what I want to know. That means that this equation will end up being a hyperbola. Okay. So a little easier way to end the notes. Okay, I'm going to be honest. Try them. Try a few. I'm going to give you some, at the bottom here of this page, I have some bookwork, I think. No, I don't even have it down. Let me write it down here. Page 923. I have 1 through 8 all, which means that's probably just looking at an equation and telling me what kind of conic section. Some of the 9 through 36 by 3s. That will give you some of the long equations and figuring them out. 39 through 43 odd will be like we just did there with our degenerates, just looking at them and doing the b squared minus 4ac. So try a few of these. I'm also going to attach a practice worksheet I've used with other students, and what I'm going to do is I'm going to attach the practice worksheet. I'm going to attach the answer key to it, and you practice how you want to practice, okay? Definitely want to do some practice on it. I do plan to put one of these, at least one of them, on the test. I want you to try them, okay? When you get to calculus, things start rotating all over. You kind of need to have some practice on it. This is hopefully going to give you just a little bit of a glimpse of it so that you're not overwhelmed later. But I'm going to be honest, it's not easy, but try it.